Okay, so let us look at our first practice. We are going to study the problem called assembly line scheduling. So let's say you are the boss of a company and your company makes Gundam models for customers. Now to assemble a model, let's say there are a couple of steps. Let's say there are n steps. For instance, step 0, you will need to get the model, and then step 1, you will somehow try to make the body of this Gundam model. After that, maybe you will build up the legs and so on and so forth. So in the end, perhaps you make sure that the model is clean and tidy, so you have a polishing step. And in the end, you want to put the model into a box so that it is ready for delivery. So this is the so-called scheduling. Okay, so we have 1 step, 2 step, 3 step, up to n steps. Okay. Now, your company is big, and actually you have 2 different factory lines for helping you to do this assembly. So there is line 1 and there is line 2. But then these 2 different lines are located at different places, and then they operate with different amounts of time for each step. So for instance, for the first line, the first step, it may take 5 units of time, and then the next one, it takes 1 unit of time, and so on and so forth. And for the second line, maybe the first step, it takes 2 units of time, and then the next one, it takes 6 units of time, and so on and so forth. So by using different line, the total time to finish the assembly process may be different. Let's say line 1, it may need 34 minutes, and line 2, it may need 38 minutes. But then, with some transportation cost, after finishing a certain step in the line, we can actually transfer the intermediate product to a different line, to the other line, by using this transportation, so that we can continue the processing in the other line for the next step. So for instance, we may start at line 1 here, finishing this, but then we do transportation and then we start the next step here. Maybe after this, we can move on, continue to do the next step here. But after that, after finishing this third step in line 2, we may take the transportation and then move on to line 1, but then to process it for the fourth step at line 1. So it can be something like this. Now, this transportation allows us flexibility to assembly the product. And then, by making use of both lines, we may be able to finish the assembly process faster. So for instance, maybe we start at line 2, and then after finishing step 0, then we will process step 1 at line 1. And if you look at this one, then it is actually better than what? Better than you start at line 1 from the beginning, right? So it will be giving us freedom or flexibility of assembling the model. So we want to ask for this question: what is the fastest assembly time? So how fast can we start at any point and then finishing at any point? So how can we do this? Okay. Now we want to solve this using this dynamic programming technique. And dynamic program usually requires a problem that can be solved by using recursion. So if this is the case, then it is better for us to think backward. And this is usually how we often solve a problem by using this DP technique. Okay, so what is meant by thinking backward? So we actually want to find out what is the fastest time or fastest way that we can reach either at the last step here or the last step here, right? So here, suppose that we know that the fastest time to finish step n at line 1 and the fastest time to finish step n at line 2. So can we tell the fastest assembly time? So if we know the fastest time that we can reach at this point, finishing everything here, and the fastest time that we can reach this point and finishing everything here, then we know, can we know what is the fastest assembly time? Yeah, then this will be really a very, very trivial question, right? Because we already know the best way to reach here and finishing this step, and also the best way to finish here, finishing this step. Then we just need to find out whichever gives us the minimum. Okay, the better will be the fastest time overall. Now let's think about one more step. So here, so suppose that we know the fastest time to finish step n minus 1. So here, this is the previous step. The fastest time to finish step n minus 1 at line 1, and the fastest time to finish step n minus 1 at line 2. Now, can we use these two information to find out the fastest time to finish step n at line 1? We know the best time to reach this point, the best time to reach this point. Do we know the best time to finish everything at this point? Now, this is actually very simple as well. Because if you want to reach this point and finishing here, either we finish at this location and then continue the processing here, or we finish at this location and then do transportation and finishing everything here. So basically, we compare the fastest time to finish step n minus 1 at line 1, and also the fastest time to finish step n minus 1 at line 2 plus the transportation time from line 2 to line 1 after step n minus 1. So we compare the time here and also the time here. So this gives us the fastest time to reach the beginning of step n at line 1, right? Now if we take the minimum of them and add the processing time of step n at line 1, then we get the answer. So in general, we can actually see something like this. So let us define some notation to simplify the discussion. We let P to represent the processing time at a certain step, and T to represent the transportation time to transfer after some step to the other line. Okay, so P1K refers to what happens in line 1. P1K is the processing time of step K at line 1. P2K is the processing time of step K but at line 2. So this is easy to remember, right? Now how about T? Okay, T1K means it is the time to transport from step K, line 1, to the other line. Okay, so to step K plus 1 of line 2. Similarly, T2K is the time of transporting from step K of line 2 to where? To step K plus 1 of line 1. So these are the input values that we can obtain for this problem. And then next we define, okay, two terms, okay, or two set of terms. The first one is called the fastest of 1K. Fastest time to finish step K at line 1, and fastest 2K represents the fastest time to finish step K at line 2. And we are going to define this and store the values of this along the way. And actually this is already the hardest part for this problem. Once we have defined these two terms, then everything will then be easy. So in general, using our discussion so far, what we know here is fastest of 1K, okay, the fastest time to finish everything at step K of line 1, it is the minimum of what? Minimum of fastest of 1K minus 1, so this is the time that we stay on line 1 after step K minus 1. And fastest 2K minus 1 plus T of 2K minus 1, this is the time that we finish the processing at line 2 at step K minus 1 and make the transportation. So the minimum of these two represents the fastest time to reach the beginning of step k. So once we have the minimum of these and add this one by the processing time P1k, then we can get the value of fastest 1k. And similarly, or symmetrically, we can get the formula for fastest of 2k. So suppose that we are now storing all the values of this fastest 1k and fastest 2k. So you can imagine that this is like there is an array for fastest 1k, so fastest 1, fastest 1, 2 up to fastest 1n. And there is also an array for fastest 2k, so fastest 2, 1, 2, 2 up to 2n. So we can have these two arrays storing the values of them as they are computed. We can actually compute fastest 1k and fastest 2k starting from k is equal to 1, and then k is equal to 2, and then k is equal to 3, up to k is equal to n. Yeah, because the value of fk, fastest 1k, just depends on k minus 1 part. Okay, so if we compute in this order, then we can get each fastest value in constant time. Yeah, because by the time we want to compute fastest of 1k, this value is already stored. We can get it in constant time. This value is already stored. We can get the value in constant time. This is input value, so we can get the sum in constant time, compare the minimum in constant time, add another input value here in constant time, so everything can be done in constant time. So that means that each of these fastest value can be computed in constant time, and there are order n of them to compute, so order n time to get all the fastest value. So which means that the fastest assembly time can be obtained in linear time.